Welcome to this module. In this module, we will look at the industrial ecology theory, which is a paradigm for sustainable systems design. So far in the course, we have discussed lots of techniques and the metrics that we can use for assessment for sustainability and sustainable systems design. So here we will go forth into what do we do after we have done the assessment, or what is the idea that we can move towards that will be ensuring the design of the systems towards more of the sustainable goals. So, just a recap, in the course we have looked into the different assessment technologies which include life cycle assessment, and in LCA we can highlight the highest impact from life cycle of product and process. When we look into the interpretation stage, it also gives us an idea the life cycle stages that have high impacts. We then looked into the thermodynamics aspect, and thermodynamics helps us understand the energy impact of any product and process, and also understanding the thermodynamic sustainability, including the work done from ecosystems in form of solar equivalent joule, or what we called as MRG. Then we discuss footprints, where we are looking at the stress on specific resources, starting from the ecological footprint, where we are looking at land as a very valuable resources, water footprint, nitrogen footprint, and global warming, which is the carbon footprint. And all of these footprint measures are actually relating the impact of human activities to the global planetary boundaries, which is the Earth system's capacity to assimilate the waste and the stressors caused by human production system. Now, in the next stage, when we are thinking about design, our main question is that how do we use all this analysis to reach the design information. So, here we are looking for opportunities for solutions rather than just assessment. So, if you think about all these environmental aspects or the impact of human activities, it is the different aspect or the kind of two faces of the same coin. What is happening is that we are interacting with the nature in terms of extracting resources from the biosphere, such as wood and food, water from the hydrosphere, and then from lithosphere we are extracting fuels and metals. The sociosphere is where the human activities or the technical activities are taking place, where we are combusting, or we are also making the processes to change the resources into valuable products for human consumption, and there is also waste treatment. Whatever is left over is being emitted to the atmosphere, biosphere, and hydrosphere. So, in a sense, your sociosphere is kind of an interacting agent, and we are just processing the resources from environment or the earth system and then dumping it back into the earth system. So, that means that in a sense we are kind of an embedded system in our whole ecological system, and if we really need to be sustainable or we want to design this system in a sustainable fashion, we need to understand how the ecological systems are working and then learn from those systems to propose sustainable design. So far as we know that lot of these designs do not account for the interactions, they just treat these systems as independently, and we design the control systems, we design the whatever the optimal parameters for it without considering the end goal of really synchronizing it with our natural systems. In most of the cases what we do is that we do remove toxic metals, which is kind of an approach towards sustainable design, but also this whole idea of recovering, reusing and recycling, or kind of creating a closed loop system within the sociosphere. What it is doing is it is reducing the interaction on both the ends in terms of extracting resources and also dumping the waste into the environment. So, in a sense we are talking that through this recover, reuse or recycle, we are going to create a closed system. But we know that it is very challenging to create a completely closed system, but that is what is the goal if we want to be sustainable, unless we realize how to create a dynamic equilibrium between all of these systems. So, the field that looks at this design paradigm is called as industrial ecology, and the reason it is called as industrial ecology because it is something what the industries are learning from the ecosystems or ecology to design their system. Lot of you may be familiar with the term biomimicry. Biomimicry is the aspect where we are observing the natural system and then we are emulating that behavior or mechanism in our technological systems. For example, we have adhesives that have been designed learning from the feet of gecko or how the gecko sticks on the wall. So, of course, there is a lot of nano processing or understanding of the mechanisms how the sticking process is happening, and then we emulate it in our technological system. Here in this case, when we are talking about industrial ecology, we want to understand how the ecosystems are behaving, because if you think about the most sustainable system that humans know is the earth system. Overall, over the years, million of years, it has existed in one form and the other form. Of course, it's not always the same form, so it's kind of a dynamic system that is changing its stability or stable state every few decades or every few millennials. So, the way ecology is defined, it is the discipline that is looking at the relationships between organisms. So, the earth system or the ecology ecosystems have lot of organisms. They have their past behavior and future environments, and all of these are interacting, and we want to understand the relationship between the structure and dynamics of the population, interaction upon species, and then also the organization of biological communities. Ecosystems studies or ecology is also concerned with the processing of energy and matter in the system, that is what is called as the nutrient cycling. So, you can see that it is a very complex system because it has both the abiotic and biotic components, so the living and the dead, which are interacting in different forms. There is a physical mechanism, there is also chemical reactions and the energy flows and mass flows that are happening. So, if you think about it, our industrial systems somehow behave like this itself, except for the biotic part where we are human beings are the biotic part. We have lot of abiotic components that we have created, which is converting the simple resources into complex resources and back into raw feedstock. So, what industrial ecology says? Industrial ecology says that it is the study of the physical, chemical and biological interactions and interrelationship both within and between industrial and ecological system. So, when we say that there is a lot of industries, let us say we have 5 different industries in a region, they all are making some product, they might be sending it to one or the other, or they might be sending it outside. Whatever the physical and chemical transformations are happening in the exchange of those products, also if there is any biological component involved such as bio-based manufacturing, which includes microorganisms, that will also be part of it. And industrial ecology is concerned with not only the study of one manufacturing plant, but the connection or the interconnected industrial network. So, here you are seeing that now instead of going from micro to macro scale where you are looking at the molecule behavior to the plant scale behavior, we are looking at the plant scale behavior to going all the way to the macro economy or the connection. So, if you remember the macroeconomic input output model, it is all about the interaction of the industrial sectors, and that is what industrial ecology focus on, in that how these industries are interacting and what kind of mechanisms are behind those interactions. Of course, interrelationship between firms as well as among their products and processes, both at the local, regional, national and global systems level, is the focus of industrial ecology field. This field has been developing for past 20 years and more than 20 years actually, and then there is emerging research that is trying to understand how these relationships can be moved towards a more sustainable trajectory. So, it is not a static system study, it is more about dynamics, but to move towards the dynamic studies, we still need to understand the steady state behavior of such interactions. And then utilizing this interconnected studies and understanding their relationship, we want to identify and implement strategies for industrial systems to more closely emulate the harmonious, sustainable ecological ecosystems. So, this is some kind of biomimicry, but at a more holistic level. And as you can imagine, when you are talking about a complex ecological system, which is itself a dynamical system interacting with industrial ecosystems, you are talking about a lot of complex interaction and multi-scale modeling that needs to be done. So, this is a field that is very complex because it is inherently multidisciplinary in understanding the interaction of different types of industries. In this module, we will learn the basics of how do we go about implementing some of the tenets of the industrial ecology, and then we will understand the challenges and barriers to implement this system. So, first we will start with the key concepts for industrial ecology. The first one is systems analysis. As you know that this is a more holistic approach to the design of industries towards sustainable trajectory. Here, instead of studying industries in one part, so instead of looking at one manufacturing plant as, let us say these are 3 industries, instead of just studying these separately, we would want to draw the larger system boundary just like in life cycle and study them as a whole. Of course, we are talking about the complete integration. So, we are also looking at how these are dependent on each other rather than just looking at how it might be independently working. Of course, their independent function has an effect on how their interaction is. Not only that, if we think about ecosystems from which these are going to extract resources, we also want that integration, so that we want to look at the behavior of the system. So, here we have expanded the system boundary to include all the systems and also the ecological systems are part of it. However, we can think that this can keep on expanding. We can think of a region, let us say state of some regional state and all the industries that are functioning in that, but it can also expand to the national scale, then from national to multinational and can global. So, there is as you keep on expanding the scope of your study, it will become more and more complex. So, to keep it more tangible, we select the system scale only as required for which we are going to make decision. But the caveat is, of course, when you are studying the subsystem and you are ignoring the effect of other larger interaction, you might not be making the right sustainable decision. Of course, we will not get into more details, but that is a caution that is always presented and is one of the aspect when you are using this kind of philosophy for design. The second aspect of the concept for industrial ecology is the material and energy flows and transformation. Since inherently when we are looking at industrial ecosystems or the multiple industries that are interacting with each other, they are exchanging materials with each other. So, your second step is to look into, after you select all the industrial connected integrated industrial ecosystem, you are going to look into the material and energy transformation. While material and energy transformation is a very simple concept that lot of students in engineering disciplines or even environmental sciences are learning about mass and energy flows, implementing it at such a large scale can become a challenge because merely about the large amount of data that is required. So, here you are systematically studying material and energy flows and also their transformations into various products, byproducts and waste throughout the industrial systems. We are not going to look into the ecological systems dynamic, but eventually if you want to also look into the overall sustainability, you would want to see the role of ecosystems in transforming those into useful or the dead weight or the dead waste. And then the last is, of course, multidisciplinary approach. Since when you are looking at industrial ecosystems, you might have different types of industry. So, I might have a plastics manufacturing industry, which is a chemical transformation, and then that could go into the packaging industry. So, your packaging industry is mostly a mechanical process of converting plastic into various kind of packaging. We might also have the energy input or the energy industry. So, you can see that your industrial ecosystem then involves the behavior of different kinds of industries. So, it is inherently multidisciplinary and you are concerned about all these 3 integrated systems together achieving the sustainable goal. So, here it is kind of a multi-scale optimization problem. It can be posed as that, and multiple researchers have actually posed the sustainability challenge into a multi-objective optimization, where each of the industries optimizing for their own sustainability goal, but together you want these industries to also move towards a larger sustainability trajectory, which is at the macro scale. More than that, we also want to understand what are the implications of policy and law on these industries to actually achieve the targets that they have set out independently, but also as an integrated system to achieve the sustainable target. So, before we get into looking into what are the challenges or how do we approach, there are three different types of systems in ecosystems that motivate the design of sustainable systems. So, the first one is type 1 or linear system. This is very straightforward. Here you have a linear process in which there is a resource input at one point, and then material and energy in final product leave the system at another point. So, it is kind of a one through flow kind of, where you have a linear through flow throughout the system. The second one is the type 2 or partially cyclic. Here some of the waste is being recycled or reused while creating another kind of waste. So, most of the industrial systems today fall into this type 2. So, most of the industrial systems independently are recycling some form of wastewater, some form of waste heat, or they are also recycling some of their co-products into different products. So, for example, the paper waste might be going into the cardboard industry. There might be some carbon waste that can be going as a filler into the building industry and henceforth. The last one is the type 3, which is the most ideal, is that here you have all the components of the system in dynamic equilibrium of something like ecological systems, and energy and materials are constantly recycled, and this is a highly integrated closed system where only energy enters from outside. So, you can see that there is nothing that is coming inside the system from outside in terms of material and nothing that is leaving the system. So, remember our first diagram where we are extracting resources from hydrosphere, lithosphere and biosphere and then dumping waste. We want to cut that off, which means that we are creating a complete closed loop and we are only relying on external energy input, maybe in form of solar energy, wind or other kind of renewable energy. So, that is the system type 2. So, for sustainable systems design, your type 3 is the ideal system. However, given the complexity of our industrial ecosystems today, it is nearly impossible to design a type 3 system. However, we still need of course more theory, we need more fundamental research into material science, we also need more fundamental research into operations of the industry towards achieving this goal of type 3. So, if you look into the system pictorially, we have type 1 system where we are assuming, which was the case before, that we are assuming we have unlimited resources. We have organism or ecosystem components, since this theory is coming from ecology. So, we are talking about organisms, but for our purposes when we are talking about technical system, these are industry, and we are having unlimited sinks for waste. So, there is a unlimited infinite sink, such as where we think of we can continue dumping waste without any impact. This type 2, you can see that you have energy and limited resources, which is what we are in today. We know that we have limited resources, we know that we have limited energy, and we are also trying to move towards limited waste, and we have different components that are trying to recycle as much as possible without creating additional waste. In the last one, which is the type 3 system, you can see that the ecosystem components, which could be your industrial systems, are completely independent and they are not dependent for their material requirement or waste disposal on any other external system. Here the only input that we require is the energy input. So, this is a completely self-reliant systems in term of material, so that we are not interacting in any way of creating negative consequences of overgrowth in terms of material consumption, but of course, there is energy will always be required. Hence, when we talk about sustainability, we say that the ultimate metric or the ultimate measure of sustainability is energy requirement. Even if you are going to create this type 3 system, how do we get enough energy to actually do that? So, now that we know that what's our goal, we are wanting to move towards system 3 for what do we learn from ecosystems to move towards that design. So, we look into the analogies that we are drawing from the ecological systems to design our industrial systems. So, the first analogy is metabolism and industrial metabolism. So, we know that ecosystems, all the organisms assimilate their food and they grow or they accumulate biomass. So, that is the metabolic activity, that is the ultimate activity that sustains that organism. So, when we are thinking about our industrial ecosystem, we can come up with the same analogy of growth. In a sense, that is an industrial metabolism, because we are consuming resources and we are using energy to actually convert it into valuable product and accompanying some waste. So, now when we are thinking about growth, all this metabolism is fueling the growth. Of course, there is also a lot of debate happening about what do we define as growth. Is the economic growth the one that we should be following, or the growth, the definition of growth itself needs to change. So, here when we talk about the growth, most of the time if you study the ecological system, there are different phases of growth. They grow slowly, then there is an lag phase, and then there is an exponential growth, and then they achieve a steady state. And of course, the system then die, one of the components will die. Similarly, when we are talking about industrial ecosystem, the first thing that we need to talk about, what is a sustainable growth? So, these are some of the open questions for design. So, I am not going to answer it in this module, but I would like to highlight it for your consideration if you are thinking about designing a system towards sustainability, by connecting into these kind of concepts, that what do you actually mean by a sustainable system. And that is a very important question before you can even say that your system is, the system that you have designed is sustainable in any way. So, first of it is, what is a sustainable growth? There is no fixed answer, everyone will come with different, and therefore, I cannot give you a metric, or I cannot give you a simple answer for what is a sustainable growth. But definitely keep it in mind whenever you are designing for any industry, and talk about that, what do they mean by the sustainability for that system. Second is the waste. Even in ecosystem, lot of the waste by one organism is kind of a feed for another one. So, we are now starting to think waste as a value added product and not just a waste. Still, globally, waste disposal, landfill, and all of the waste reutilization is a big challenge and not really solved yet. So, waste as value added product in every system, we need to think when we are designing, what is the waste being generated, and can it be used as a value added product, or can there be processing that can be done to make it a value added product. The third is efficiency. Of course, efficiency has been around in the systems design for decades, and since the field of design has been there. So, the more and more we improve the efficiency, the more sustainable we think we can be. However, there is a contradiction here. If you think about the natural systems are not really that efficient. There is a lot of dissipation. So, here there is a conflict between the way natural systems are operating, and if we are going to mimic those systems for industrial ecosystems. So, some of the questions that we may ask is that, how do organisms sustain themselves, how do ecosystems sustain themselves, and is efficiency an important aspect for the sustainability. The next important analogy that you would want to think about for sustainable industrial ecosystem design is the symbiosis. So, symbiosis is a very predominant way in which the natural systems are existing together and sustaining to each other. The definition of this symbiosis is that it is a mutualistic beneficial interaction that helps both the interacting components achieve their goal. So, now of course, plants do not talk to each other or microorganisms, but there is also research that there are chemical signaling that is happening, and that is beyond the scope of this module. However, when there is a mutualistic interaction between different organisms, there is some certain goal that each of those organisms is actually trying to attain. Similarly, when two industries are interacting, they both have this kind of interaction. So, if we want to design a more sustainable industrial ecosystem by considering all the interaction, we really need to think about what is the goal of each of the component, and how are these maintaining both of those, and identifying more and more symbiotic opportunities, so that we can make them interact in certain ways and move towards the sustainable design goal. So, industrial symbiosis will form a very important aspect of sustainable design. So, the way industrial symbiosis is defined is that it is a basic feature of implementing industrial ecology. it develops the mutually beneficial interaction between the participating industrial entities, and it is also known as byproduct synergy network, where the waste or co-product from one industry becomes the resource of the other industry. So, this is a very basic concept. However, you will see that implementing it in practice or using it in design becomes a real challenge. Here is an example of industrial ecosystem. This is in Kalundborg, Denmark, and this has been organically developing for over the years. Organically developing means no one sat and developed a design for that industrial ecosystem. Same as like ecosystem, if you let some plants lie on some organic matter, you will see that after some years or some days, maybe months, there is a flora of different kinds of plants that have developed. There may be fungi, there might be like a whole consortium or whole complex ecosystem that develops. All of that happens organically given the right food, fuel, and also the right kind of environmental condition. So, of course, that what is right condition is defined, cannot be accurately defined, and that makes it very hard for you to tell what kind of ecosystem will develop. In industrial ecosystems, what has been observed so far is that something like that happens. There is an organic interaction. So, in this case, what happened was that there is an oil refinery and electric power station, and oil refinery started giving gas to it, but electric power station, they were very close, and they realized that they have an extra steam that has some residual heat power that can be used as oil refinery. What that meant was that for oil refinery, now they needed to burn less and less coal to actually do the heating. That was a mutually beneficial system for them. What is the benefit that electric power station may have got from it? Maybe some economic incentive or some mutually reduction in the cost of the gas from the oil refinery. So, this happened, and then they realized that they could do the same thing with other industries. So, municipality of Kalundborg, they realized that they do not need that high quality heat, they just need a lower quality heat for the heating of their houses. So, they started buying the waste heat from electric power station, and then their waste heat, whatever was left, they could give back to electric power station. That led to reheating of the same steam. So, that caused another mutually beneficial synergy between those two systems, and you can see that there were multiple types. So, if you have to design this kind of system in a region or a nation, you are not focused on one kind of system. It is inherently a multidisciplinary system. We have power generation, oil refinery, we have the chemical manufacturers like sulfuric acid and cement manufacturing. We also have the local farmers who were using some of the waste fish culture as a sludge for their farming practice, and the fish was actually dependent because this was a heated pool tank where they were growing fish and for consumption, and they were using the waste heat. So, this is kind of a network that develops, and here you can see that if you look at the food tropics in the ecological networks, it is very similar to that. There is an industrial metabolism in a sense that there is waste, heat, and the industrial material flows that is happening, and it is kind of developing a network to reduce the overall resource dependence on external sources. So, this kind of system actually is moving towards that sustainable industrial ecosystem design. However, as you can see that it is not very easy to think about this. One reason, of course, is the lack of transparency into the industrial operations, which has been a major bottleneck for this kind of systems to develop. What we will do is we will do a very short activity to see the benefit of such industrial symbiotic network, and then we will go into the challenges and barriers. So, let us look at this activity. Here we have two industries, industry A and industry B, and industry A requires feedstock, about 20 kg of feedstock per kg of product. It is making 10 kg of product, and it is creating about 10 kg of waste per kg of product. Similarly, industry B requires 10 kg of feedstock per kg of its product. It is making 5 kg of waste, 5 kg of product, and it is creating 5 kg waste per kg of products. So, in this case, the idea is that the waste of your industry B can be used to replace the feedstock of industry A, and there is a perfect one-to-one substitution. So, when there is perfect 1-to-1 substitution, we can say we can substitute the feedstock by the waste by in the equivalent amount. Now, let us see what the challenge is. So, our industry B is actually paying money for waste disposal. So, here the motivation towards looking for additional opportunity to dispose their waste would be to reduce the cost. So, since it is paying $1 per kg of waste disposal, if it is making 5 times 5, 25 kg of waste, it is paying about $25 for their waste disposal. So, that is an economic cost to the industry B. And it also produces 0.5 kg CO2 per kg emission in the process. So, you do have emissions going on. Industry A, what it does is that it recognizes that industry B has a pain point, that it has probably very less, it is paying for waste. So, it is kind of eating into its profit. So, industry A develops a process, being innovative here is important, develops a process to process the waste to replace their feedstock. And what it does is that, and then industry B gets to know it. So, industry B is now willing to pay $0.2 per kg to industry A. So, here the smart thing for industry A is that it creates the environment conducive for industry B to consider this proposition, and on the other hand industry B is thinking about that I need to pay less, significantly less, about 80% less to process per kg waste. So, and the feedstock cost for industry A is of course $2 per kg. So, now if it is going to use the industry waste B to replace feedstock, it is going to pay very less. It is going to of course replace $2 per kg with $0.2 per kg, and that kind of win-win scenario is very conducive to the formation of industrial synergy between A and B. So, let us take 30 seconds and calculate the economic and environmental benefits of this industrial symbiosis that may develop between industry A and B because of this new process that industry A has developed. So, let us look into the solution. So, here the feedstock requirement it requires 20 kgs of feedstock per kg product. So, it requires 20 kg of feedstock multiplied by 10 kg it is making. So, we require about 200 kg of feedstock. Okay. And how much it pays? So, cost of this feedstock about $2 per kg. So, we have $2 multiplied by 200, which means initially it pays about $400 for its feedstock. Let us say how much waste available from industry B. So, the waste available is about 5 times 5. So, we have about 25 kg of waste available, which means that industry A can get 25 kg from B. So, we get 25 kg at $0.2 per kg cost, and then it can reduce its purchase of feedstock by 25 kg, and that one it needs to get at $2 per kg. So, our new cost for industry A will be, this will be $5. and this is about 175 into 2, which is 350. So, we have about $355 cost of feedstock. So, okay, I think the wording was different. The wording is that industry B is actually paying $0.2 per kg. So, here we are not, the industry A is actually getting this much benefit by using that 25 kgs. So, our actual cost is not $355, but it is actually $345. So, you can see that for industry A, you have a net saving of 400 minus 345, or which is equal to $55 of net saving. So, here it is an economic profitable proposition for industry A to actually get the waste from industry B, because industry B is paying them to get that waste. What is the benefit for industry B? So, industry B, benefit to industry B, we can see that so there is some waste disposal cost. Let us look at what is the waste disposal cost. So, industry B pays $1 per kg for waste disposal, which means that initially it was paying $25 to dispose, and now it is only actually paying, new cost to them is only about 25 into 0.5 or 0.2, which was about $5. So, the net benefit to industry B is about $20. So, $20 it is saved, and therefore, it is a for both the industries, it is a economically win-win scenario to create that synergies. So, identifying these kind of economic benefit or the mutual benefits to two industries is the conducive environment to create such industrial synergy. We can also calculate the environmental cost in the same way by looking at the avoided emission. So, since if you look at the industry B, when it is disposing, it is causing 0.5 kg CO2 per kg emission. So, the total avoided emission, because now it is not disposing it. So, total avoided emissions by industry B in this case is 25 kg was being disposed and 0.5 kg CO2 was being emitted. So, that is about 12.5 kg CO2. So, this is the amount of CO2 emissions that are avoided because of this industrial synergy. So, people have seen these kind of benefits in developing these industrial synergies, following the same approach of how the ecosystems work in mutually beneficial ways, and has led to creating of this industrial symbiosis network, or what they also call as eco-industrial parks. So, of course, this looks like a no-brainer to do it, that this is where we should go in terms of sustainable systems design when we look at the macro scale, but then what are the challenges? So, before we get into challenges, we'll look into the steps to identify industrial symbiosis. So, now that we have an idea of designing sustainable systems by looking into the industrial symbiosis, let us look at what are the ways or steps to actually identify these industrial symbiosis. When you are implementing industrial symbiosis to create such industrial ecosystems park or industrial networks, first we think about opportunities for lessening impacts. Remember that our goal is to move towards type 3 system, which is a completely closed system in terms of material flows. So, we are looking into zero emission systems. So, you might have heard about this term called net zero, which is inspired by thinking about reducing the waste completely. And in waste, we are also talking about emissions, because we want to not even emit emissions to the environment, which are also considered waste. So, that is why there is a push on the carbon capture technology, so that we can reduce the emissions of CO2. Second is material substitution. We do not want to create waste that are going to be very toxic and do not have a way to be recycled. So, we are trying to shift to renewable and biodegradable material, so that it does not accumulate as long term waste in the environment. Third is the dematerialization and decarbonization. So, both dematerialization and decarbonization are a very interesting concept from the aspect that we want to make the products, but we want to reduce the amount of product input or the material input that is going into it, and also the improving of the reduction in the carbon input that is going in the system. There is this idea also of functionality economy that people are thinking, where you derive more function with less material, which is definitely some aspect of the product design that is happening to reduce the material intensity of each of the products. The second is material flow analysis. Since industrial symbiosis is inherently looking into the material and waste flows, which is also talking about the industrial metabolism, material flow analysis at the macro scale network is also very important. From the concept perspective, it is a very easy concept to comprehend. However, doing a material flow analysis for the whole economy or at the larger industrial ecosystem scale has been challenging. There are increasing amount of efforts in doing research on developing MFA for the regional economy in the industrial ecology field, and there is developing literature. The method is simpler, but we need to be more innovative in getting the right data and at the right scale to be able to develop these MFAs. Then cost analysis of recovery. So, there is a concept called Sherwood plot, which talks about if we have these kind of information on the cost analysis of recovery to create this closed system, it can tell us where do we invest our efforts to go towards sustainable design. Then we can also do the same kind of analysis in terms of thermodynamic analysis for recovery, which is done by looking at the thermodynamic cost required for the recovery. Then there are these aspects that you may look at. One is the physical proximity of synergy. Of course, if you are going to spend a lot of time into transportation, that may not benefit the industrial symbiosis very well. So, you may have to think about the logistic life cycle of products, which also thinks about where is the end of life and how it is being recycled. Then we need to think about the indicators. We have talked about a lot of metrics and we can develop some new indicators, but this is also an active area of research to understand how do we say that a system is actually moving towards the goal of type 3. And then we can also learn from the already available industrial ecosystems that have been going on for long. There are a lot of eco-industrial parks that are being developed in different countries across the world, including US, Europe, China, and we can learn from those advancements to see that what would be the right design in a particular region. So, let us look at the lessening impact. So, zero emission system is that we are creating more closed loop. Carbon capture and sequestration systems is something that is a very prominent one in this area, and we can have a whole full course on carbon capture and sequestration systems, because there are numerous technologies that are being accounted for. Recycling of metals is another very active area, especially for the critical metals which are in very short supply. Material substitution, biopolymers is one of the important aspect. It may not be good for ecological footprint because it requires land area. So, therefore, we need to look for alternative material substitution wherever we are finding stressors in the system causing damage to the ecosystems. And one example would be also waste reinforcement of roads that has been happening. Actually, in India, there are a lot of places where they have been using the waste plastics into forming concrete and forming material that are used in the pavement. That is one example of actually lessening the impact towards the industrial synergy. Dematerialization is another aspect where decline over time happens in weight of the materials used in industrial end products, or decline in embedded energy, which means that you are putting in less and less energy per unit of that product being formed. From environmental viewpoint, the dematerialization should be defined as the change in amount of waste generated per unit of industrial product. So, that is another way of thinking about how do we incorporate the concept of dematerialization in the sustainable system design. So, for example, our laptops got smaller and phones got larger. So, what is the limit for combining all functionality? Computer engineers may be looking for a day where you can do all your computations on a mobile phone and we won't need the laptops or the big screen computers. So, or we might be using multifunctional screens and just do all the computations on your handheld devices. That is also a very active area of research and an example of dematerialization. However, there is a downside of that, because now when you are creating these miniature systems, it is very hard to recycle. So, is dematerialization, if your design towards system 3 is taking care of dematerialization, you need to be cautious that it should also take care of recycling at the end, so that you do not have those challenge of dumping all the time. Here there is a picture of dematerialization. You can talk about different aspects of dematerializations. Of course, you need to think about the quality of the product, also the ease of manufacturing. So, if you are doing a design towards dematerialization, you need to look into the production cost. If because of dematerialization your production cost becomes very high, it can become prohibitive. Can we repair or replace? If you are creating new products for that idea of dematerialization and the size and complexity. So, if you open your phone, you can see that it has become more and more complex. Earlier the watches were very simple, now the watches have become even more complex, because now they are serving multifunctionality. So, the more and more you are reducing, moving towards dematerialization by improving the functionality in one component, you might be increasing the size and complexity. So, inherently in such kind of sustainable systems design, there is a trade-off. Since we can, for each of the system that you are looking at, these aspects would be unique. So, we can use this as a guidance to understand the effect of dematerialization on our goal of sustainability in terms of type 3 system, with the additional challenge of what may happen on different parameters that are associated with dematerialization. So, here is an example of reducing steel. You can see that as the years have gone by, different kinds of products are now making basically consumption of carbon steel by the end use has gone down, even though the consumption may have go up. So, you can see that in motor vehicles it used to be 19.5 and it has, by 1982 it was about 10.6. That does not mean that the number of motor vehicles being manufactured were reduced. It was just that the better and better product design came that utilize less and less steel for formation of motor vehicles. This can be talked about any kind of industrial product that we are designing today, so that we can move towards the goal of dematerialization. So, if you are taking into account of sustainability for a product design, dematerialization can be a good parameter that you can think of to improve the product design towards sustainability. We can also decouple growth with energy and material. So, here you can see the energy intensity of different economies. You can see that all the economies, most of the economies actually had a reduction in energy intensity from 1973 to 1985. Australia reduced 6%, which means that it is making the same amount of, it is utilizing less and less energy per output of GDP. That may not be true today, because now our society has moved towards a very highly energy intensive society. Now we are using mobile phones, computational structure much more than the past economies which were more mechanical. So, this might be true that today we might be decoupling growth from material by dematerialization, but energy we might be coupling more and more, because now we are more energy reliant, and hence energy susceptibility becomes a very important parameter for your sustainability of the system's growth. The second one, where material flow analysis is a simple concept. Here you can see the flow of platinum through various product systems. So, this is a simple MFA that was published by the Scientific American long back in 1989, and you can see all it does is that you can track all the materials that you are extracting and the way it is flowing into different products. Now, this again you can see that here you have the ore that is being mined going into mining and refining, metal fabrication, forming metal products, then there is chemical conversion, automotive catalyst manufacture, automatic catalytic converters, some of them is going into chemical catalysts, petroleum catalysts, and 12% is recycled, about 88% is being lost. So, here this is platinum, and if you want to think about the number of materials we have hundreds of composite materials in circulation today. If you want to really understand, create a closed loop type 3 system for industrial ecosystem for all of those composites, it will take a lot of time to do those MFAs. Hence, there is a global effort in creating those MFAs, and industrial ecology researchers are pushing forward to really understand how can we get these data and information readily available for use by engineers, so that it can be used for informing the design systems. The next aspect is cost. So, here this is a Sherwood plot that was developed back in 1980s, and you can see what it does is that on the x axis is the dilution, and on the y axis is the price that is we pay for per pound of that extraction. So, here you can see that the more dilute the stream is, the higher cost for extraction is. That is also the same challenge of direct air capture. So, you are talking about extracting CO2 from a very dilute parts per million atmospheric concentration, and it is a very costly technology. That has been the challenge of implementation of direct air capture. In the Sherwood plot, you can see that based on the cost, you can identify which of these streams are actually amenable for your region to develop the industrial symbiosis. So, I might be thinking that my region really needs this medicine penicillin, and the cost of making true raw penicillin is really high. So, what we would do is that we know that there is a waste stream that has penicillin that can be recovered and purified. So, we can spend about $100 per pound of penicillin. However, penicillin cost is actually very less, so that is not a very good example, but of course, radium, uranium, and also sulfur, bromine from seawater, those are some of the components. So, if you are thinking about going towards sustainable systems design and you have a waste stream which has composition of multiple components in it, what you would do is you would calculate the price per pound of extraction and compare it with the virgin resources, which is the raw resources that you might be getting from elsewhere. If the price comparison suggests that this is a beneficial synergy that can develop, then you will go about it, otherwise not. The challenge today is that we have too many waste streams that are not economically viable, and hence the move towards the design of type 3 system has been a very slow process in current scenario. The next one is we can develop the same kind of plot. This is a more recent one that was provided by Professor Tim Gutowski at MIT in mechanical engineering, and instead of looking at, since we talked that energy is going to be the ultimate metric or the ultimate cost for making or sustaining systems, we are using the embodied energy. So, remember in our life cycle calculation, we calculate the embodied emissions and embodied resources and embodied energy as well. So, here instead of looking at the cost, I am saying that what is the life cycle and embodied energy in the resources. So, I have already spent that much of energy in making this product that is now available in the waste. So, here if your on the y axis is your embodied energy, on the x axis is your dilution level or the availability of the or what concentration it is available in the waste stream. You can see that the embodied energy in platinum is really high, because platinum is a resource that requires a lot of intense energy to purify. Even if it is available at this much dilution and the embodied energy is high, when I go about designing a sustainable synergetic system, I would probably go for extracting the platinum, because it has very high embodied energy, and I would not want to spend that much energy again in making platinum. Both cost and energy. So, instead of just embody, we can also have the cost here. So, on the same graph, we could plot the cost of each product, and then we can compare and kind of come up with a trade off. So, we can look at the trade off between energy and cost at certain dilution level. So, here you would need to know that how much energy you have already spent and what is the new cost that you are going to. If the energy cost is really high, of course, you will be going for the one that has higher embodied energy. The challenge with our today's society is that energy has become very cheap and we are wasting energy to get lot of products and then wasting it without thinking about the impact on ultimate energy resource restriction that we may face. So, now that we have learnt about different ways where we can think of developing industrial symbiosis, where we are thinking about lessening the impact, decarbonization, dematerialization, energy cost, economic cost and all of that aspect, material flow analysis. Let us think of what are the challenges. Why do we not have, even we have the theory available, why do we not have such industrial symbiosis across the world? There are very small pockets of the world where these kind of sustainable systems achieve, and in future we would want to have these industrial systems all across the world. So, the first problem is the institutional barrier. So, the waste market information is something that is missing. We have this information. So, this is actually what today we can solve with the data and the AI revolution is availability of this waste market information. If this waste market information is consistently available, that will provide us with information on the opportunities. There are of course legal issues because different countries have different rules and regulations. Lot of time if the waste quality is not really, it's going to bring in additional toxicity into product formulation, that may be a complete no-no. So, understanding of the legal issues is another barrier. We have regulations, so lot of the regulatory things have not been very forward thinking in understanding for the adaptability. So, here what we need to know is that really understanding how industrial ecology concepts of looking at the whole macro scale and designing by understanding the cost and environmental benefit of those synergies, how do we understand, link it to quality assurance as well. So, that may involve including the cost of quality assurance for production. So, for ensuring a long term industrial symbiosis, there are risks associated. Now, you think about like previously your industrial firm was just operating alone. So, kind of you have a control system that is only working on this one, but now we have a network of systems. So, we have a lot of different systems that are working in dynamic equilibrium, and now you are thinking about the risk. So, of course, any risk that happens to this particular firm can be cascaded to this one. Chemical engineers are not oblivious of such concept because we have been thinking about the cascading impacts of any perturbation. So, this is kind of a perturbation may happen at each node and may transfer to whole of the industrial synergies. Now, the challenge is that how do we recover from it? So, they are not ready for new regulations. What we need to then do is identify the concept of resilience, and we know that concept of resilience has been used for plant design for multiple years in the past. So, what is resilience? So, resilience is the property of the system by which it bounces back from a catastrophe or a major change. We have seen in like most of the chemical plants, we have steady state controllers, we have the set points, and if there is perturbation, your plant kind of regulates and comes back to that steady state point. Similarly, when we are designing our industrial ecosystems, we would want to identify what is the stable state that it might operate, what are the different perturbations that it can come through, and then identify what will be the new steady state that it can perpetually go into. Natural systems have the same issue. You might have seen lot of ecological systems burn down during wildfires, but then after few years or after few months, you will see that life re-emerges. So, that is a very resilient system. It might emerge in a different functional form. So, we can expect that whatever industrial symbiotic system we are designing, it might collapse in its current form, but it might attain a new steady state. So, we can make it more diverse, we can make it more resilient to perturbation by increasing more and more flows in. And here we have to use the concept of network science. The quantitative methods of the development of industrial symbiosis are not very different from network analysis, multi-scale optimization and the process control, but in this course I will not go through all those fundamental details because there are multiple courses that cover those basics. With that, let us revisit what industrial ecology is. We are thinking about a new paradigm for design of sustainable system, which is that we look at industrial systems as part of an industrial ecosystem where all the industries are interacting with each other in terms of matter and energy. We use the key concept for determining the opportunities for IS or the industrial symbiosis, which is systems analysis, material and energy flows, multidisciplinary approach, and then we are thinking about going towards the type 3 system, which is a completely closed system. We have learned the industrial ecology tools like life cycle analysis and material flow analysis, which we can use to identify these synergies, and if at the life cycle scale some synergy does not make sense, then it would not be the ideal option. And also last, I think we need to really think about the resilience in the design when we are designing this system. However, at this point, the design of industrial systems is at very infant stage in terms of identifying what theories we need to use for implementing this. But we have all the basic concepts and paradigm and ideas that we can use to start these design. So, I hope that through this course you are able to realize how you can go about designing a macro scale industrial ecosystems by using different tools and techniques like life cycle analysis, footprint methods, and then this theory of industrial symbiosis to be able to design macro scale industrial ecosystems. So, thank you for visiting this module and also learning from this course, and good luck for your journey on sustainability.